Hello everybody, this is Chapter 6 on weathering and soils. So as a basic definition, weathering is a process needed for sedimentary rocks to form. And so it predates the rock itself. It's a precursor for sedimentary rocks. It involves the physical breakdown called disintegration and or the chemical alteration called decomposition of some previously existing rock of either or of sedimentary, igneous, or metamorphic nature, which is at the surface or really close to it. These broken down rock later gets eroded, it gets transported, and then it gets deposited as sediment towards the formation of a sedimentary rock in the future. We refer to the area outlined with the red oval as the weathering process. And you see that weathering can happen to all three types of rocks, and that the end product overall is going to be their weathering, meaning the weathering of the rock into sediments. So they end up always making a sedimentary rock after a few extra steps of lithification, which involves a few things that we'll look at in Chapter 7. Sedimentary rocks to form, a few steps need to occur, namely those 7 steps that I have outlined in the slide. There needs to be a pre-existing rock that is uplifted to the surface. The rock needs to either get disintegrated, broken down by physical processes, or it needs to get decomposed, which is altered by chemical processes, or maybe it's a combination of both. There, on step 3, is where weathering has its importance. Once the rock is broken down or altered, the sediments are transported and deposited in the environment of deposition, which will be the place where there will occur future lithification, which means rock making itself. During lithification, the sediments get compacted and cemented, which makes this new sedimentary rock. So I'll refer to the 7 steps again during Chapter 7 when we talk about the sedimentary rocks themselves. And I'll refer to it during the exam and the final exam as well, most likely. So again, weathering takes place on step 3 here, and that's why we are touching based upon this little flowchart. When we think of weathering, we think of external processes, surface processes that affect the rocks which were created by some internal process within Earth's depths. Or rocks that were created at or near the surface by processes going on within the sediments that make them up. So hence kind of internal in a way. Weathering itself, again, is the breakdown or alteration of a previous rock, as I had said in the first and second slide. It tends to be a relatively slow process to human eyes, so it is easy to underestimate sometimes. But it is a key step to sedimentary rock making, and it is also very important to us humans, as many of the sustaining minerals and elements that are found in the soil, which is ultimately where our food comes from, were originally put there by the processes of weathering, or at least they were freed up from solid rock by the processes of weathering. They also create very spectacular scenery, like the one that we see in many of the Utah National Parks, and they affect many of the buildings that we make as well, like you're seeing in the picture on the left. Many of those buildings that we make get weathered away very easily, and so we need to take this into account. Weathering, as I had said before, one of them is physical or mechanical, it's called, and it's mainly disintegration. And the second one is chemical, and it's mainly decomposition. Okay, so in physical weathering, the physical agents break down the rock into smaller and smaller pieces without changing the rock's mineral composition. In chemical weathering, there is a chemical transformation of those rocks into one or more new compounds by the chemical reaction of the rock's mineral composition and any agents, like it could be water or it could be air from the atmosphere in which to which the rocks are in contact with. Many times, weathering and erosion are terms that can be interchanged, but they should not be. okay? They should not be, because they're different things. Erosion is the removal and the transport of already weathered material. Weathering is just a breakdown or alteration of the rocks, okay? Okay, so as an example, the rock that makes up the cliffs on the picture on the right is getting broken down by the wind and the water that are hitting it. And afterwards, the sediment is being removed from the rest of the cliff by the waves. Later on, the sediment gets carried away to a different location. So it's being eroded as the waves are, taking it away from the cliff and transporting it somewhere else. But it's getting weathered just by the water that, infiltrates the grains and by the wind that makes them weaker. Another example here is a piece of paper. So, in the example on the left, the piece of paper gets shredded and hence torn into smaller and smaller pieces. Those pieces, however, are still made up from the same particles that make up the larger piece of paper. So here we're exemplifying physical or mechanical weathering. Okay? On the picture on the right, the paper is getting burned. So the elements and compounds that make up that piece of paper are being transformed to create just CO2 and water, basically. So they're going to escape as gases. So overall, there is a transformation of the chemical composition of the paper itself. Okay, so now we're going to go a little bit into detail on mechanical weathering. We'll cover the different processes of mechanical weathering, and then we'll cover chemical weathering. Okay, so when a rock undergoes mechanical or physical weathering, the breakdown of it into smaller pieces causes an increase of the surface area of said rock or rock volume. When there is a further area that is exposed to the surface, chemical weathering can easily attack it, or more easily attack it, because it's easier for the agents to touch the mineral composition of that rock, which makes sense. As an example of this, for example, you take an Alka-Seltzer, right? I think that's what it's called, which are basically when you eat too much and your stomach is not feeling so good after like a barbecue or something. You take this Alka-Seltzer. I don't know what you call it in English, but I think that's the same. If you dissolve these Alka-Seltzer from a whole tablet, for example, it takes about a minute or two for it all to dissolve. But if you buy the powdered from the store of the Alka-Seltzer, then it takes several seconds to dissolve, not a minute or two. This is because there is a greater surface area in all of the powdered pieces combined than in the single tablet. So the water around either particle size can only start dissolving the parts that it's in contact with. So at times, both weathering types kind of act together. Again, physical breakdown, making the first step towards the chemical alteration to take the lead afterwards. Physical breakdown breaks down the pieces, then chemical weathering is able to alter the composition of them. Okay, so let's look at the example that's on the slide. The cubic rock on the left has a volume of 2 hypothetical units. Let's call them meters by 2 meters. So it's a cubic 2 meter by 2 meter by 2 meter volume. Okay? So overall, there are 4 square meters on all of the cube's sides. There are 6 sides to the cube, as in any cube, making the overall square meter that are exposed to be 24 square units, or meters, I should say. Okay? So this would obviously be the case if the rock was kind of levitating in the air, because one of those sides is going to be touching the ground and most likely attached to it. But let's assume that the rock is kind of levitating and it's still in contact with water and air, which are agents of weathering. Okay, so again, in that first example, a 2 meter by 2 meter by 2 meter volume, cubic volume, is going to have 24 square meters exposed to the surface. in the next image over, if that previous cube is split into 8 equal pieces, so the combined volume does not change, each of these 8 pieces has a 1 square meter on each side of the cubes. And each cube again has 6 faces, so each cube has 6 square meters exposed to the surface, which makes the cumulative meters that are exposed to the surface to be 48, because there are 8 cubes. So again, 6 square meters per cube times 8 cubes that now make up the same volume as in the previous image make up 48 square meters that are exposed to the surface. Okay. As you move on to the next image, each of those 8 previous cubes pieces are split into 8 more. So again, the combined volume does not change. It's still the same volume. Each one of those 8 pieces has a square meterage of 0.25 square meters per side of each cube. And each cube has 6 faces, just like any cube. So each cube has a combined exposed surface of 1.5 square meters, right? But now we have 64 cubes that make up the volume. So if we multiply 64 times 1.5 square meters, we get a combined exposed surface of 96 square meters, okay? So you see that every time you split all those cubes into split them up into 8, which would be splitting each side of the cube into 2, it makes the exposed surface increase twice, which is amazing. So overall, again, you see that although the volume does not change, the overall surface exposed grows dramatically every time that the rock is broken down into those smaller pieces.